In our paper, Simple but Effective, Clip Embeddings for Embodied AI, we present competitive performance on navigation-heavy tasks in embodied AI using frozen visual representations from Clip, and investigate this effectiveness. This work has been conducted by researchers at the Allen Institute for AI. Embodied AI is a growing area of research in which agents are trained to solve tasks in physical and simulated environments. These embodied agents learn to interact in their environments given sensory inputs. For example, an agent might walk around a scene based on what it sees with a camera. A few examples of tasks in embodied AI are point navigation, where an agent must navigate to a coordinate, object navigation, where an agent must locate an object, and room rearrangement, where an agent must move objects to match the original state of a room. Here is a high-level model diagram for common embodied agents. An agent will receive RGB input from its camera and have a goal, in this case, find laptop for the object nav task. The RGB image is processed by a visual encoder, here the CNN, and this visual encoding, the goal, and a hidden state are passed to a model employing an RNN. The model selects an action, such as movement, and the agent follows this action, updating the environment, and the process repeats until the agent selects the done action. At this time, lightweight ResNet models, either trained from scratch or pre-trained with ImageNet, are most commonly used as the visual encoders in embodied agents. Separately, CLIP introduces vision and text encoders trained contrastively on 400 million image-text pairs. These models have been shown to be highly effective at zero-shot image recognition, for example on ImageNet. They have even presented improvements across many other tasks in computer vision, such as open vocabulary object detection and text-driven image manipulation, as visualized here. Buoyed by the success of CLIP across computer vision, we investigate if CLIP is also beneficial for the domain of embodied AI. So, we conduct a series of experiments where we train baseline agents using DDPPO with frozen ImageNet pre-trained ResNet 50 encoders, and compare them against frozen ResNet 50 CLIP encoders. We compare these models in 4 experiments, covering 3 different navigational tasks and across 2 simulators, Thor and Habitat. In all cases, we find significant gains between 3 and 10 points when using CLIP's encoders. Here, we show leaderboards for the RoboThor and Habitat object nav tasks, comparing our highlighted CLIP baseline model against other top methods. We find the performance quite competitive. Our model even beats the winners of the 2021 Habitat Object Nav Challenge. This is particularly impressive because, unlike these entries, our model is an incredibly simple baseline with no task-specific architectures, inductive biases, auxiliary training tasks, or depth maps. We include additional leaderboards for the other experiments in our paper. We ask why CLIP representations are so much more effective than ImageNet representations. So, we design a collection of linear probing experiments measuring how well their visual representations encode the following semantic and geometric primitives: object reachability, object presence at a location, object presence, and free space. We visualize these primitives here and detail them further in our paper. Our experiments indicate that CLIP encodes all 4 of these primitives more effectively, and we find this especially interesting due to CLIP's semantic training, objective, and distributions. Lastly, we are hopeful that agents can also utilize CLIP's text encoder for representing goals in conjunction with images. We conduct a zero-shot object nav experiment with the visualized architecture, where an agent sees 8 object types during training and is expected to find 4 unseen objects at test time. We are excited to see some success here and to have established an initial baseline for this task. We demonstrated the effectiveness of CLIP representations for navigation-heavy embodied AI tasks, even beating specialized architectures at some challenges. To diagnose CLIP's effectiveness, we studied how well these representations encode relevant primitives for navigational tasks, and found that CLIP models outperformed their ImageNet counterparts. Finally, we also leveraged CLIP to enable an initial baseline for a zero-shot object nav in RoboThor. We anticipate exciting future investigations into improved visual representations for embodied agents, as well as further progress on the zero-shot object nav task. Thank you.